Unlike a lot of the other advent of code problems, problem 15 pretty much requires you to know about one of a couple of algorithms to solve it. For most of the previous ones, you could just come up with solutions off of previous experience, cleverness, or looking through multiple different types of approaches, but for this one you pretty much have to use an algorithm because this problem is at its core just a shortest path problem. And since it operates on a weighted graph, you cannot use breadth first search, which most people probably know about. And so today I'll be talking about two algorithms that you can use for this. Dijkstra's algorithm, which is faster, and Bellman-Ford, which is easier. So let's look at the problem statement first. We have a grid which has a risk level for each square, which is invoked when we step onto the square from another cell. And we can move sideways, both horizontally and vertically, but we cannot move diagonally. And the risk is only invoked when you walk onto the cell, so you do not count the cost of the first cell, the top left one where you start. And this also means that traveling between a cell, the edge cost is variable depending on which way you're going. And so your goal is to find the path with the lowest total risk. So in the example given here, it's bolded or highlighted in white. Now, even though the path always goes down or to the right in the example here, this is not generally true of the problem, and it isn't said anywhere that you have to do this. And so we have to consider moving left and upright as well. So you cannot use dynamic programming for this. You have to use a pathfinding algorithm. So firstly, I'll go over an implementation of how you could do this in Python using Dijkstra's algorithm. So we're going to skip straight past part 1 because it's just a subset of part 2. For part 2, we have to consider a grid that is actually 5 times larger in both dimensions. And our original tile, which is highlighted in white here, gets copied 5 times sideways and downwards. And each time it moves either right or down, we increase each of the risks correspondingly by 1. So this is an example using only 1 by 1 subcells. And if we exceed 9, we wrap back around to 1. So let's just get our puzzle input, and we can... There. So that is our data, and now we first need to process it into a grid of numbers, and so we're going to do list map of int over each row in this string. Okay, and so we've parsed our data into a 2D grid of numbers. So in order to get this effect with the 5x5 tiling, what you could do is you could basically try to extend your existing list, or what I actually find easier in Python is to just build a grid that is already larger than, that is of the right size, and then just use indexing. So what we're going to do is we're going to make a grid. What did I call the previous one? Data? Yeah. So we're going to make a grid whose width is going to be 5 times the... So first of all, the grid is a square, so let's just call side length is equal to data length of data. We're going to make a grid that is 5 times side length by 5 times side length. And then we can just iterate for I in range SL times 5, for J in range SL times 5. We can just apply an index. So here the grid index at ij is going to be equal to the data index at I mod side length times at J mod side length. And so that would just create a tiling without doing any modifications. But in order to account for that, we just add I plus j, because I is the number of times, sorry, I divided by 5 plus j divided by 5, because that's the number of times we've tiled it to the right. And to wrap around, we just modulo 9, except since we wrap 10 to 1 and not 9 to 0, we have to offset by 1 before doing our modulo. And so this will give us our grid tiled as needed. And just to demonstrate this, let's try this with a smaller data size first. Let's just do 1, 2, 3, 4. we can see that our grid sorry, this isn't meant to be divided by 5, this is meant to be divided by the side length. We can see that our grid does tile. So the first row 1, 2 gets tiled to 2, 3, 3, 4, etc. And then as we go down 1, 2, 3, 4 gets tiled to 2, 3, 4, 5, which gets tiled to 3, 4, 5, 6, etc. And we see that we wrap around here as well. Okay, so now that we have our grid, let's implement Dijkstra's algorithm. So Dijkstra's algorithm solves the single source shortest path problem. What that problem asks is, given an arbitrary graph, let's just draw an example out here. Given an arbitrary graph and a starting node, what is the shortest path to every other node on the graph? So that's what Dijkstra's algorithm solves. Now, since it can get the shortest path to every node, it can also get the shortest path to a target end node, which is what we're going to use it for here. The way Dijkstra's algorithm works is it greedily selects the cheapest node that is available to visit at every step. In the beginning, there's only one node available, the starting node with a cost of 0. When we select a node, we add all of its neighbor nodes into our priority queue. A priority queue is basically just a special data structure that always keeps the smallest element in the front, which is how we can greedily select the cheapest element. And it is much faster in terms of time complexity than if we were to sort the list at each step. So after we visit this node, we will mark it as visited, and then we will identify its neighbor nodes and put those into our priority queue. So that's one step. For the second step, we identify the cheapest node. That's this one because it has a cost of 3, which is cheaper than this node. So we mark this as visited and then look at all of its neighbor nodes. Since this one is already visited, we do not go back to it. So we get 6 here. Now, let's just say for the sake of argument that this edge actually has a weight of 1 instead of 5. So you might notice that this path here was identified first, but this is not optimal because this has a cost of 6, whereas this path has a cost of 5. But that's not to worry because the Dijkstra's algorithm will greedily select the cheapest node, which is actually this node here. And after we visit it, we will add this node into our open priority queue again, but this time with a cost of 5. And so when we visit this node again, we're going to visit the 5 cost path of this node, not the 6 cost path of the node, because it is a greedy algorithm. So we select this node and we assign it a cost of 5. And then, oh yeah, I forgot to mention, when we look at this node, we'll add this one to the open set with a weight of 11. And when we identify this node, we'll add it with a weight of 7. So Dijkstra's algorithm will greedily select the 6 here actually. Even though we can tell that we shouldn't visit this again, the program will still pop it off of the priority queue. And so since this node has already been visited, we just need to remember to ignore that. And finally, we look at this node and we'll greedily select the 7. And once we've found the end node, we can just exit the program and we know that the shortest path is length 7. Specifically, the path that goes along these edges. So that's the high-level description of how Dijkstra's algorithm works. In Python, we have a utility called heapq. It comes with a bunch of functions, but the only ones you actually need to know are heapq.heapPush and heapq.heapPop. HeapPush takes a heap and a value, and heapPop takes a heap. The heap here is just a standard Python list. As long as you use the heapPush and heapPop functions to modify them, the list will stay in the relevant order that the heapq utility needs to manage the priority queue. Basically, just don't modify the list yourself. And so when you heap push a value on, it costs O of log n, where n is the size of the heap so far, to get it into the right position. And then when you do a heap pop, it costs O of log n to take the smallest node and remove it from the data structure and return it to you. Note that this is much cheaper than if we were to manually sort the list at each step, which would be O of n log n for each push and O of n for each pop. or I guess O of 1 if you do it efficiently. Okay, so Dijkstra's algorithm requires us to have two things. Firstly, actually it only requires us to have one thing. We need to have, in addition to the PQ, the graph itself must be represented as an adjacency list. Basically, for each node, we need to be able to have a list of neighbors. That's what an adjacency list gives us. And internally, the Dijkstra's algorithm will maintain a priority queue and a visited set. Now, since we're operating on a grid, we don't actually need to manually get an explicit adjacency list. We can just look for neighbors. And so we're going to start with our priority queue, which will initially contain one node. So since we want to greedily select by the cheapest cost, then we want to put the cost at the front of our element in our priority queue, so that Python's lexicographical ordering will keep it in order. So initially we start at the cell 0, 0 with a cost of 0, and our visited starts out empty. It is important to not put the starting node into your visited set, because otherwise it'll actually just skip your entire graph. So while we still have nodes to visit, we will pop off the current top of the priority queue. Cost x and y is heap_q.heap pop pq. If we've already visited x, y, then we can just continue the loop. And otherwise we will add x, y to our visited nodes here. And now we look at the neighbors. So for next x and next y in, the possibilities are we could go up, down, left, or right. If it's not in bounds, so if nx or ny are less than 0, or they're greater than the side length, then we skip it. If we've already visited it, then we skip it, and otherwise we will add it to the priority queue. It's important to remember not to add your nodes to the visited set when you identify them here, but only after you've actually visited them. This is because, as we saw with our example, the first path we find might not necessarily be the best path. We will visit the best path first, but we might not necessarily find it first. And so here we just add it to the priority queue. So heap_q.heap push priority queue, and the value we push is cost plus the weight of our edge. I'll replace that later, and the next x and next y values. The weight here, it's just the cost of stepping onto that grid space, and we know that the cost of traversing to a grid cell is just the risk factor at that position. In other words, it's just grid at nx and y. And the final thing to do is, this will keep running until eventually it's identified the cost for every single cell, but we don't care about that, we only want to know about the destination. So if x equals y equals side length minus 1, so if we've hit the bottom right corner, then we've found our answer, so we just print the cost and exit. And so we get our answer of $589. I was expecting it to give me this is the part 1 answer. Why is it giving me that? Oh, my bad. Because side length minus 1 is the bottom right corner of the original grid. It would have to be side length times 5 minus 1. And so that gives us let me just fix the boundaries. That gives us our final answer of 2,885. And we see that it ran in just under 2 seconds, so it's a pretty fast algorithm for something that's checking a grid of size, what is it, 500 by 500? Yeah. So that's how you could implement this using Dijkstra's algorithm in Python. Now let's look over how to do this with Bellman-Ford, and here I'll switch over to using JavaScript. The reason I even looked at the Bellman-Ford algorithm is because a friend of mine was trying to solve this problem in JavaScript, and it doesn't have an easily accessible heap or priority queue utility like Python does. And so eventually, after trying to get Dijkstra to work, I just recommended that he used Bellman-Ford, and it actually worked pretty well. So what does Bellman-Ford do? So first, let's get this setup done in JavaScript. So data is this thing dot split new lines dot map. For each row, we take the listified row and map it over parse int. Okay, and so that gives us our data. So we're going to do a similar thing with the grid. Does this work in? Okay, so that doesn't seem to work in JavaScript, right? Oh, I forgot. You can just do this, right? Yeah, okay. So we're going to do a similar thing to what we did with the Python solution. And basically we're just going to do for I it goes from 0 to side length times 5. For the same thing for j. And then we can just do at the top of our outer loop, we're going to do grid I is a new empty list, and then inside here we'll just do grid ij is equal to data at I mod sl at j mod sl plus I divided by sl plus j divided by sl minus 1 mod 9 plus 1. And so this should give us our tiled grid. Let's just check it out by replacing our data. So if we try it with 1, 2, 3, 4, we see that we get 1, 2, 3, 4 tiled to 2, 3, 4, 5, etc. And the repetitions and wraparound work perfectly fine. So now the idea behind Bellman-Ford is that it runs on a similar principle and it solves the same problem. It is objectively slower than Dijkstra's algorithm, but it has a caveat that I'll talk about in a bit. So let's redraw our graph from before, with this as our starting node still, and this is our ending node. So Bellman-Ford starts by first saying that the distance to every node is infinity, except the distance to the starting node is 0. Now at each step, it will check every single edge, and it will say for each edge, is it cheaper to go to the first node and then cross the edge to the second node, or is it cheaper to just visit the second node from whatever path we had before? So let's just do a couple iterations and hopefully this will begin to make sense. So on the first iteration, we would look at each edge. So for this edge here, we see that, okay, if we go from here to here, that gives us a cost of 4 because it's 0 plus 4, which is less than infinity. Same here, we get 3. This still gives us infinity, so none of these will change anything. And so at the end of our iteration, we now have these updated node distances. And so we just repeat that step again. Nothing changes here, nothing changes here. This gives us 6 here. And then it's promptly overwritten by this giving us 5. This gives us 11. And that would be the end of the iteration because this node was previously unvisited, so this edge wouldn't find any results. And then if we run another iteration, none of these edges change anything, but this edge will give us another improvement, which sets this node to distance 7. And if we repeat this one more step, nothing changes, and so we know we can exit our loop now. And so just like with Dijkstra's algorithm, this has actually given us a shortest path to every single node. And we just need to read off the one for the end node. Now the trick to Bellman-Ford that makes it actually exist as an algorithm when Dijkstra's is better for this for applicable purposes is that Dijkstra's algorithm breaks when you have negative cycles in your graph. Because if you have a negative cycle in your graph, Dijkstra's algorithm will actually give you the wrong answer. If your graph contains a negative cycle anywhere in it, then the optimal cost to get from any node to any other node is negative infinity. Let's say we want to get from this node to this node. We just go here, walk around the cycle infinitely many times, and then just go here. And so the answer will be negative infinity for every single node. So if there's a negative cycle, the result from Dijkstra's algorithm is completely meaningless, and Dijkstra's algorithm has no way of knowing that. Bellman-Ford is actually able to detect these negative cycles. I won't go over this in depth today because it's out of scope of this problem, but that's the reason why Bellman-Ford is actually used. It's to detect negative cycles in graphs. But the advantage to this is, unlike with Dijkstra's algorithm, we don't need a priority queue or any complex data structure for that matter. All we need is arrays. So we're going to do a bit of pre-processing on our grid here. To do Bellman-Ford, you need a list of vertices and a list of edges. Specifically, not a list of vertices, but you need a mapping from each vertex to its distance. So since we're on a grid and each vertex is a coordinate, it would make sense for us to keep our distances as a grid as well. So let's just make side length by 5 times 5 by side length times 5 grid, where each node starts off with a cost of infinity, except the first node. And now we want to also pre-process that into a list of edges. So on this graph here, I showed you bidirectional edges, but with this problem, since the edges have different costs going both ways, we have to keep it directed. So in order to check for edges, it's actually not that hard. So as long as we're not on the left in the top row, so if I is not 0, or I is greater than 0, we have one edge, which is the edge from the node above us to the edge to the current node. So edges.push, we're going to store the edge as a triple. It's going to contain the start node, the end node, and the cost. The start node is the node above us, I-1j. The end node is our current node, ij, and the cost is grid at ij. Same deal, if we're not on the leftmost column, then we can come in from the left with the same cost and end node, of course. If we are not in the bottommost row, we can come up from below. And if we are not in the rightmost column, then we can come in from the right. And now we just need to run Bellman-Ford. So while true, we're going to keep a flag indicating whether or not anything has changed. Once nothing changes in one loop, re-looping won't do anything, so we can just exit at that point. So we will loop through each edge, so for var edge of edges, so the start node is edges 0, end node is edges 1, and weight is edges 2. If it is cheaper to get to go to the start node first, and then walk across our current edge, than it is to go to the end node using the path we've currently found, then we will update the distance. And mark our updated flag to true to indicate that we have made a change. And once we have no more changes left, we can just break out of the loop. And so once this loop is done, we have stabilized our Bellman-Ford state, And so distances will actually contain the shortest path to every single node on the grid. This is a bit overkill, but in the worst case, Dijkstra's algorithm would do the same, and there isn't actually a better way around it anyway. So now we just need to read off the distance to the last node, which is just, of course, distances side length times 5 minus 1, side length times 5 minus 1. And so this is... Ooh, what did I do here? Cannot read property. Okay, so start is... Oh, my bad. This is meant to say edge, not edges. Okay. And so if we leave it to run for a bit, we get our answer of 2,885. So even though this is worse than Dijkstra's algorithm, it's arguably easier to implement. If you know Dijkstra's algorithm, Dijkstra's is actually shorter and faster to implement. But Bellman-Ford, especially because of the processing, it took a bit longer. It doesn't require you to know heap queues, and it's a lot simpler to remember. You basically just repeatedly update each edge to see if there's a better path to every node, and once you're done updating, you can just read off your answer. And so even though this is a slower algorithm, it still only took just under 3 seconds to run, so it's actually not that much worse than Dijkstra's algorithm. Okay, so that's how you would solve it, both using Dijkstra's algorithm, using Python as an example, or with Bellman-Ford using JavaScript as an example. So lastly, before I end this video, what exactly is a priority queue and how does it work? So a priority queue really only has 2 requirements. You can insert arbitrary values into it, and the popped value will always be the smallest one. It could also be the largest one if you want a max priority queue, but usually people go with the smaller one. So how would you implement this? Well, priority queues are typically implemented using something called heaps, and this probably isn't surprising given that the module name for the Python utility was not priority queue, but heap queue. A heap works like so. It is a binary tree that always makes sure the elements, each element is smaller than its children. So basically it is sorted it is sorted vertically. The order of its siblings does not matter, so the 4 and 5 here could be swapped, but as long as each node is larger than its parent, we are fine. And so now how do we update our heap? So let's say we start with this configuration here. So we can see that the ordering of children across also doesn't matter. So the 3 is smaller than the 4 here, but it doesn't matter because 3 is larger than its parent, and 4 is larger than its parent and smaller than its children. So this relationship does not matter. So let's say we want to pop off the topmost node, so the 1 here. So if we just go ahead and remove it, now we need something to fill this gap here, right? If we move up the smaller of its children, that would work. But now we have to move up its children as well. And in this case, that works okay. But what if these children were placed like this? Then we move up this child, and then we move up this child. And now we run into a slight problem here. There's a gap left here. A heap needs to be, or should be, a maximum binary tree. That means that each layer is filled before the next one starts, and the layers are all filled left to right. And I'll explain why this is important later on. So that doesn't work so well. First of all, because it's hard to keep track of, and second of all, because you might end up with gaps. So how do you fix that? Well, what we can do is there is only one element on this heap that can be removed without creating problems, and that is the last element. But we can't remove that because that's not the one we want. In fact, it's not even the largest, so how is that helpful? Well, if we swap the top element with the last element, now we can pop the last element off and just save it for returning. Now this isn't a heap anymore, but the shape is correct. And as long as we only swap elements, the shape will maintain correctness. So we look at 7, we see that it is not in heap ordering. That is, it is larger than one of its children. So to fix that, we swap it with the smaller of its children. That ensures that it doesn't break ordering with the other 2 elements that get reordered. And we see that this is still not in heap ordering, so we swap it with the smaller of its children. In this case, it only has 1. And so now this is back into heap ordering. We see that each element is smaller than its children, and the gap is in the correct spot. Now let's say we want to insert an element back in, the 1. We just tag it onto the end, and it's not in the correct position, so we compare it to its parent. This step is actually easier. If it is smaller than its parent, then we just swap them. And we just keep doing that until it's found its spot. And let's say we wanted to insert a 2 here, we tag it onto the end of our binary tree. We perform the swaps as necessary. And we see that this is in heap order and the shape is correct. Each layer was filled up before the next one, and the incomplete layer is packed to the left. Why is this ordering important anyway? Why is the shape of our tree relevant? Well, let's read off the elements just row by row and assign an index to each of them. 0, 1, 2, 3, 4, 5, 6, 7. Notice one interesting thing. If you look at any node, n, its children are 2n plus 1 and 2n plus 2. This is helpful because it means that from any node we have a very easy way of getting its parent, which is floor divide n minus 1 over 2, and both its left and right children. And since we just gave them indices in ascending order, we can now flatten this heap out into a list and use this relationship with the indices, so we do not have to store a data structure. And this is very important because it makes heaps quite optimal in memory. In fact, they take the same amount of memory as storing the list itself. So since JavaScript is the one that's missing this utility, let's implement a heap in JavaScript. So we'll implement 2 functions just like the heap queue library had. We'll have heap push, which takes an array, a heap and a value, and heap pop, which takes just a heap. So let's implement the push first because it's easier. So to push, we first need to just get the index of where the element will be inserted. So let's insert the element first, just at the end of the heap, heap.pushValue, and the index is going to equal to the length of the heap minus 1. That's the last index, and therefore the index of our value. And now we just constantly perform a check. So the parent index is, like I mentioned, the floor of index minus 1 over 2. And so while the index is greater than 0, because once it's hit 0, it doesn't have a parent anymore, while the index is greater than 0 and the value at the index is smaller than its parent, which is illegal, we will keep swapping. So we'll first swap the index and the parent in our heap, and then we will set index to parent because that's where the element moved, and obtain the new parent index, like so. So what this does is it will first insert the element just at the end of the heap and then repeatedly check and compare. If the current value is smaller than its parent, we swap them and move on and keep checking. And for the heap pop operation, we first need to swap the top element to the bottom. So swap heap 0 heap.length minus 1. We can pop the last value off now because that won't affect the shape, and we'll save it for returning. Heap.pop, return val. And then we need to constantly check it against its 2 children. So while it is greater than either of its children. So if it's greater than the first child, we need to check for 2 things. First of all, that the first child exists. So let's set index equal to 0 initially because we are heapifying from the top down. While index times 2 plus 1 is less than heap.length, and heap at index times 2 plus 1 is less than heap at index. So basically, if the left child exists and is smaller than the current node, or if index times 2 plus 2 is less than heap.length, and heap at index times 2 plus 2 is less than heap of index. So if the right child exists and is smaller, then we need to perform a swap. Which one to swap to? Well, if the right child doesn't exist, then we don't swap to it. Or if the left child is smaller, then we will swap to the left child. So swap heap index times 2 plus 1, and then index is equal to index times 2 plus 1. And otherwise we swap it with the right child. And before we call it a day, we need to do one last thing. The rest of this code kind of breaks when the heap is empty. So if the heap's length is only 1, we want to just return heap.pop. And we're basically done. So let's try it out. Let's start a heap and then heap push some random value, and let's just push all the numbers from 1 to 9 in some arbitrary order. Okay. So that's all of the numbers from 1 to 9. And now while heap.length is greater than 0, console.log heap pop heap. And just like magic, the elements come out in the correct order. So with this, it's admittedly a bit tedious, but it's not a bad idea to just take this code and save it for the future if you need priority queues for whatever reason on AOC in the future, or just if you're using JavaScript in general. I believe there's a Node library specifically for this. You can probably look one up and find it. Of course, installing Node libraries while you're doing Advent of Code challenges is a bit annoying. So yeah. To summarize the explanation of heaps, basically it is a data structure that makes sure that each element is smaller than its children and thus always has the smallest element at the top. And to push, we just insert it at the end and filter it into the correct place, which takes only maximum number of steps that takes is the height of the tree, which is logarithmic time. And to pop an element, we just swap it with the bottommost element and then filter the top element down into the right place, which again has a maximum complexity of log n. And so using this, we can maintain a list in sorted order and thereby implement a priority queue. So hopefully you learned something out of this. We went over the Dijkstra's algorithm in Python, the Bellman-Ford algorithm in JavaScript, and a brief explanation on heaps and how you can implement them in JavaScript if you need them for Dijkstra's in JavaScript as well. So thank you for watching this video, and I hope you enjoyed.